I expect you know about this. As the syllabus tells you, I purposely build a considerable amount of earnable extra credit into every quiz and exam. This stuff is tough. And for those of you who really succeed in getting at this stuff, I want you to have the opportunity to show me that. And for those of you who work hard, but may not necessarily get on top of all this stuff, because this stuff is difficult. It took me a long time to get on top of this stuff, years and years. And I want to share my knowledge that I have of this stuff with you this term. I don't want you to have to wait years and years. But some of you may take longer than this term. It only took me about 40 years. That's why I do this kind of stuff. Build in the earnable extra credit. Base value 75 points, but up to 133 points earnable. So if you make the 133 points, that's what goes down in the scorebook. There's no percentages and there's no out ofs. Never mind the junk in Sakai. I've been fighting with the Sakai operators ever since they foisted upon me this unfortunate version of gradebook maintenance program. Because it insists, Sakai, on calculating grades based on percentages. I do nothing with percentages. If you make the point total that corresponds to a grade of A, which is shown you in the syllabus, I don't right off the bat remember the value. You've made an A, period. There's no out ofs. No statistics, no curves, no percentages. Do you know that from a curve standpoint, a true curve standpoint, if the most common percentage achievement in a class is 90%, that sounds pretty good, don't you think? If the most common percentage achievement is 90%, more people got 90% than any other score. That's a C. That is a C by true curve. I don't do anything with this curve stuff. Because the situation I just described to you is not what happens. We don't wind up with that kind of achievement. Instead, we often find situations which are very unfortunate, where frankly the class is not taught a particularly high level, but yet the most common performance on a percentage basis is 45%. So that becomes C. Well, the hell with that. I'm not doing anything with that. So I say, look, if you make this many, you've got this grade, period, end of story. So at the minimum, I hope you recognize that what you see in Sakai, from the Sakai standpoint, is not what I see. Total points is what counts. You want to know where you stand, you add up the points you have. No percentages, no fancy arithmetic, assuming you can add. And I'm going to believe that you can do that. Okay? I say that because I'll have students who, for example, on the first quiz, because they don't understand what I just said yet, and they'll make over 75 points. And they'll say, what's my percent? And I say, I don't know and I don't give a damn. But clearly it's above 100% relative to the base value, isn't it? So forget that percent junk. Forget that Sakai is a stupid system which I have to live with. Total points, nothing else matters. Okay, now then. To give me an idea what kind of information you come here with from 2045. Information that I need you to know about. Lewis structures, to get at properties of molecules, Important properties of molecules like bond energy, stuff like that. One of the questions in the discussion part of Quiz 1 is following the top half of Quiz 1, which is multiple choice format, just to get you in the habit of dealing with the exams. $20 points. There's a question that will ask you about the strength of a carbon-carbon single bond compared to the strength of a carbon-carbon triple bond versus the strength of a nitrogen-nitrogen single bond compared to the strength of a nitrogen-nitrogen triple bond. Now after I wrote the damn quiz, I forgot there's a part of this I didn't put in. So I'll tell you about it right now. If you address this part, I'll tell the graders to give you more points, more credit. Okay? When you look, well, let's do it. You got your notebook. Look at page, 2319. Finally got there. Did you look at tables of data like this in 2045? And be asked to understand what this information means? And how you can explain it? That's what counts. You may well have looked at information like this in 2045. What I'm curious about is if you were asked questions like this. So the part of this question that I forgot to write on the quiz. Take a look at the carbon-carbon single bond. Let me see. Delta HD value. Okay? You know what delta HD stands for? What's delta HD stand for? Bond dissociation enthalpy. The energy required to break a bond in what fashion? Homolytically or heterolytically? See, you didn't learn about this in 2045, did you? You heard about it, but you didn't learn about it. I keep telling those, what the hell are you doing? These people come here, they don't know any chemistry. And it's not your fault. I'm going to keep screaming and hollering. I don't know if it'll do any good. I've already made the bold statement to some people. If I had my way, every person who comes here to study chemistry, every person who comes here and has to take 2045 would take this course from one person and one person only. Guess who that person is? Me! And this nonsense that's going on in that course where you're not learning chemistry would disappear. This stuff is wonderful. And I want you to realize how wonderful it is. All right? You're looking at this carbon-carbon bond dissociation enthalpy, 348 kilojoules per mole, versus NN, 163 kilojoules per mole. First off, based on electronegativity, you should find that to be unusual. Why? Nitrogen atoms are more electronegative. That means they are expected to stabilize electron density to a greater extent. That includes bonding electron density. Yet this information is showing you a carbon-carbon single bond is a good deal stronger than a nitrogen-nitrogen single bond, right? Breaking the bond homolytically means, for an NN bond, this time I'll use a pair of two dots to simulate the bond because I want to tear this in half. If I break this bond homolytically, I break it like this. I tear it up so I create atoms, not ions. That's all it means, okay? But this information is showing you. To break the carbon-carbon bond, it costs you a lot more than breaking the nitrogen-nitrogen bond for the single bond. Now while you're looking at this table, look at the carbon-carbon triple bond and the nitrogen-nitrogen triple bond, which you find in nitrogen. A couple other molecules, but nitrogen for sure. What happens now to these bond strengths? Hell of a lot stronger for NN, isn't it? How about that? Can you explain this stuff? That's what question 20 is. That's what this question, which is worth 20 points, is about. To answer this, I will expect to see Lewis structures, and I will expect to see comments relevant to these bond energies, which follow from the Lewis structures. That's all I'm going to say for now. On with finishing the part of chapter 18 which leads up to and through the material for which you'll be responsible tomorrow, which is question 1810, writing equations for reactions. And then in the remaining time permitting today, we'll start to talk about the quantitative aspects of Bronsted-Lowry acid-base chemistry. In the main, in regard to analyzing equilibrium systems, quantitatively analyzing, because we've laid the foundation now which allows us to get at that stuff. We got through C last time. Here's D. D says, what chemistry occurs if you dilute aluminum nitrate solution, water of course the solvent, end of story. What chemistry occurs if you dilute this solution? We could apply this to any water solution of any weak acid or weak base. What chemistry will occur if you dilute the solution, which means you're adding more solvent? Do you realize that this reaction equation tells you, if you read it left to right, if you read it this way, okay? It tells you for hydrated aluminum ion to get together with water to make hydronium ion and this stuff, these things have to do what? They have to collaborate each other. They have to collide. That means if I take this system as it exists and I add either additional hydrated aluminum ion or water, because when I dilute I'm adding water, have I increased the chance for this collaboration to occur? Hell yes. Believe me, in a given stretch of highway, if I put more cars, I got a better chance for an accident to occur. It's not what we want, but that's simply the truth of the matter. Okay? So we know by adding solvent to this system, the reaction which occurs to get us back to equilibrium is left to right or right to left? Left to right or right to left? This is the one which goes. If I add this or this, okay? Now then, how many of you are mystified by this formula? Or have you recognized that hydrated metal ions constitute a special category of weak Bronsted acids? If you look at our acid-base table, you'll see a few hydrated metal ions listed in the acid column. And of course hydrated metal ions also in the base column because they're the conjugate bases of these hydrated metal ions. You'll see hydrated iron plus 3, you'll see hydrated aluminum plus 3, you'll see hydrated zinc plus 2, you'll see hydrated magnesium ion. I don't remember if there's any others in there. There are additional hydrated metal ions in the acid-base table that you see in the laboratory manual, because you will investigate these hydrated metal ions by the chemistry that you do in laboratory. 46L. Okay. For starters, you see this label on the bottle, okay? And as usual, when you see a label on the bottle, what the label tells you is how the solution was prepared. It doesn't tell you what's in the solution. You have to know chemistry to know what's in the solution. If I take this solution, as you folks will do in laboratory this term when you go to assignment 4, and observe pH, you'll find out that the pH of this solution is about 3. Where did this hydronium ion molarity come from? Well, it couldn't have come from nitrate ion, could it? Because the acid-base table tells you nitrate ion is a base. So if it reacted as a base, the pH would go up, not down. But nitrate ion is a base weaker than water. So nitrate ion really in water solution does not affect pH. Does not change the hydronium ion or hydroxide ion molarity of the solution. Well, then it follows that if this solution is showing me a pH on the order of 3, it's got to be something to do with aluminum ion. And the something to do with aluminum ion is a consequence of this being formed when this solution is prepared. Because aluminum ion, like many other metal ions, has a rather substantial positive charge density. You all learned about mass density. You know, mass per volume. Well, this is charge density. Now, the best way to look at charge density is not charge per volume, because the inside part of a chemical species is not where the chemistry occurs, it's on the surface. So we'll call it, really, charge density is more a surface area phenomenon. If I want to get the charge density of this, I'm going to measure the radius of aluminum ion, calculate its area, and divide this charge by that area. That's how I'm going to size up the charge density for this thing, because it's a surface density. Do you think because this ion is pretty small, do you believe it's pretty small? Do you realize that aluminum ion, take a look at aluminum ion, is derived from aluminum in period number 3. You know that aluminum ion is isoelectronic with the neon atom? What's isoelectronic mean? The same electron configuration. Neon and aluminum plus 3 are isoelectronic. They have the same electron configuration. I could include in that statement fluoride ion, Na plus, Mg2 plus, and a whole bunch of other ions, which are also isoelectronic with neon. Is neon pretty small? You learned about size trend patterns in 2045. Neon is not only pretty small, it's the smallest atom in period number 2. How does the size of aluminum plus 3, all by itself as an isolated ion, how must the size of aluminum plus 3 compare to Ne? Got to be even smaller. This damn thing's got 13 protons pulling on that configuration. Neon only has 10. Well then, I'm looking at an ion which is pretty small and got a charge of plus 3. That means its charge density is considerable. So what do you think happens from a Coulomb standpoint? You learned about Coulomb's law in 2045, didn't you? I don't know. What does Coulomb's law say? Coulomb's law says between oppositely charged particles there is a strong force of attraction if the charges on these particles are rather concentrated. That means charge density. Okay? And Coulomb's law says for like charged particles, if the charges on the particles are rather concentrated, there's a strong force of repulsion. Well, here's our water molecule meeting up with an aluminum ion because you put this stuff in solution, you dissolved it. It's an ionic compound, it dissociated an Al plus 3 nitrate ion. So these things are now in the system. They meet up with these things. They conk into the negative end of the water dipole, which is the oxygen atom end where you've got non-bonding electron density. Do you think there is a positive force of attraction between these species? You're damn right. It's sufficiently strong so as to form this, where 6 water molecules wrap around each individual aluminum ion and make this. Now then, the shorter and stronger is this aluminum ion water molecule bond, an ion dipole bond. The greater is the force of repulsion between the centers of positive charge. What do I mean by centers of positive charge? Well, here's Al plus 3. That's a center of positive charge. And the hydrogen atom ends of a water molecule are also centers of positive charge, right? Because these are the positive parts of the water dipole. So this is repulsion. And the stronger is this repulsion, the easier the OH bond breaks. Breaks heterolytically. And off in solution travels H plus. And the H plus in the water solution gloms on to another water molecule, and voila! hydronium ion is produced. That accounts for the acidity of aluminum nitrate solution or similar solutions. In any case, that's discussed in the notes if you have not yet paid attention to it. Although this should have been offered to you in discussion class last week. Last week. Okay? In any case, we now recognize why the addition of solvent to aluminum nitrate solution causes this reaction to occur left to right. Well then, we can go to E. E says, what happens if I evaporate acetic acid solution? I could ask the same question for evaporation of aluminum nitrate solution. I could ask the same question for removal of solvent from any solution of a weak acid or weak base. Weak Bronsted acid, weak Bronsted base. Well, if we recognize that adding water makes it go this way, what's going to happen if I remove water? Go the other way. That's all. No big deal. So this is for E. And if you write the acetic acid equilibrium, acetic acid, AQ plus water, double arrows, hydronium ion AQ, acetate ion AQ. You remove water from that, the reaction which occurs is to travel back toward reformation of acetic acid. And of course, in the attempt of the system to replace the water that you took away, because this reaction also makes water. Enough said. F. Potassium hydroxide solution, sodium bicarb solution. Well, let's go back to fundamentals. You know that to tackle any case like this, what do you got to do first? PSI, absolutely. You got the PSIs written? This is K plus. AQ if you want to put the tag on there. HO minus AQ. Na plus AQ. And bicarb ion, whose formula I prefer to write like this when I write the formula for the ion by itself. Because this formula does a much better job of corresponding to the actual structure of bicarb ion than this thing. You know the reason, don't you? If I give you this formula, HCO3 minus, and I ask you to get at the most important property of this species, which is its structure, many of you, because you're just learning, will make the mistake of writing a Lewis structure where the hydrogen atom is connected to carbon, and that is wrong. So I keep asking these textbook authors, what the hell are you doing this for? You know what they tell me? Well, they know that. I said, what are you talking about? If they know it, what the hell are they taking this class for? You idiot. What you're doing is appealing to the people who teach this damn thing, but don't really want to teach it. That's true. The biggest thing that's wrong with general chemistry is that most people who teach it don't know enough about it to teach it. How about that for a statement? And anybody who wants to take me up on this, I'm here, I'm ready, let's go get them. And I'll beat the hell out of them. I mean it. You're looking at a person who firmly believes that I understand this stuff for general chemistry better than anybody else in this world. That includes MIT. I've looked at all their general chemistry lectures. They got stuff in there that's followed up. MIT, UCal, Berkeley, you name it, you bring them on. Because I made a career of this stuff. And when it comes to solution chemistry, and I will tell them straight away, there's no more important chemistry in the world than chemistry that occurs in water solution. If you don't believe me, let's let the blood out of your veins and I'm going to pour in gasoline. And see how well you do then. They shut up and go away when I hit them with stuff like that. Because I'm going to hit them with what's fact. Not something I believe without foundation. I'm going to hit them with real evidence. That's what counts in science. And that's what I want you folks to come to grips with. Because this stuff is wonderful. Ha! All right, back to this stuff. And of course, water molecules for each. Now you know what we do after we got the PSI. as necessary, you use the support of the acid-base table. You pick out the strongest acid in your PSI and partner it up with the strongest base, also selected from your PSI. Because if any acid-base reaction at all is going to occur in this system which you're going to prepare, which for this case is a mix of this solution with this solution, it's got to involve the strongest acid given H plus to the strongest base for appreciably concentrated species. Nothing fancy about this. It's just horse sense applied to the system. No more, no less. And not one damn general chemistry textbook does this. So I ask, what the hell are these people doing? I have no idea. I mean it. Well, I do know what they're doing. They're interfering with learning chemistry. That's what they're doing. They're standing in your way. They're preventing you from getting on with legitimate knowledge of this marvelously important subject. And I object. Now then, let's get past the sermon and return to the chemistry. You got the acid-base table? Pick me out the strongest acid from this inventory. And I'll write it down. What is it? Here it is. The hydrogen carbonate ion. Have you noticed in your acid-base table that certain formulas appear in both columns? Hydrogen carbonate ion is one of these. Hydrogen carbonate ion, though, is a particularly unique species regarding its appearance in both columns. Because hydrogen carbonate ion, there's a couple other species like this in the table, but hydrogen carbonate ion is most common. I bet you got hydrogen carbonate ion at home. You got any at home? You got any of this orange box? Maybe you got a big box, I don't know, with a circle on it, Arm & Hammer on there. Sodium hydrogen carbonate, that's what it is. They call it baking soda. Big deal. So if you got baking soda at home, you got this stuff. It is a stronger acid than water and a stronger base than water. How about that? Cute, isn't it? A few other species exhibit this same property. All right. Strongest base? Hydroxide ion. So we know how the game plays. This is the reacting acid. This is the reacting base. This gives H plus to this. And in so doing, we make water as the product acid and carbonate ion as the product base. And the last part of the game is tell me about extent. Extent is large because, as the acid-base table shows you, this stuff is a stronger acid than water. We already told you that. We just told you that. Okay? And, of course, hydroxide ion is a stronger base than carbonate ion. So extent equals large, or is large, whatever you want to write down. Okay? All right, now let's play this game again. Kind of. In the kind of part, I mean we're going to again consider sodium hydrogen carbonate. Uh-oh. Sodium hydrogen carbonate solution over here. But this time we're going to mix it up with sodium hydrogen sulfate. So, we've already got the inventory for the sodium hydrogen carbonate solution. Now let's write the inventory for the sodium hydrogen sulfate solution. Water, of course, sodium ion, of course. And so far we've looked at formulas for species, which are there, but they're not important to us now, because these species, which are in the solution in abundance, don't participate in any chemistry in the system we're going to create. But I'll write it over here. The last species, which we find to be in this solution in high concentration, which follows from our inventory, because sodium hydrogen sulfate is also an ionic compound. You got any hydrogen sulfate ion at home? Did you ever at home use a product for cleansing? Maybe your parents did. Maybe you saw them do this. Mom, you used dad, I don't know. Sanaflush? Vanish? Sanaflush and Vanish are the same product. Different names, but the same chemistry. potassium hydrogen sulfate. What does the acid-base table tell you about hydrogen sulfate ion? What does the acid-base table tell you about hydrogen sulfate ion? It's a pretty strong weak acid, isn't it? Okay. We'll tell you about the significance of its strength, which depends on its Ka value when we get to that stuff. Okay? So in this case, that is to say for system G, the strongest acid which follows from our inventory is this stuff, isn't it? What's the strongest base? What is it? It's hydrogen carbonate ion. How about that? So what we're seeing is an illustration of system F where hydrogen carbonate ion behaves as an acid versus system G where hydrogen carbonate ion again is a principal species, but now it's behaving as a Bronsted base. Okay? And bases are H plus grabbers. Now before we complete this reaction equation, we're going to run this. We're going to run this system right here and now. Beaker, kind of smudged up with chalk because of my chalky hands, so what? Sodium hydrogen carbonate, half molar. I took some from the lab. Your lab, our lab. General chemistry lab. What a nice slug of that in there. And now, sodium hydrogen sulfate. Before I add the sodium hydrogen sulfate, I want you to tell me what we will see on adding the sodium hydrogen sulfate solution to the sodium bicarb solution which is already in the beaker. Bubbles. Are we going to see bubbles? Why are we going to see bubbles? Are you looking at the acid-base table? When you look at the acid-base table, are you seeing this formula? You see this formula in the acid-base table? The quotes mean that this stuff is not true carbonic acid. This is hydrated CO2. And you'll see a note at the bottom of the acid-base table which tells you about this. This stuff is not very soluble. Pardon me, it's not very stable. Not very stable in water. And when this stuff isn't very stable, it decomposes into what? Water and CO2. Is CO2 particularly soluble in water? Yes or no? No, why not? Why is CO2 not very soluble in water? Gas. Ammonia is a gas under normal lab conditions. That's damn soluble in water. You can make ammonia solution up to 16 molar. Why is ammonia very soluble in water, which is a gas under normal lab conditions, whereas CO2, which is also a gas under normal laboratory conditions, is not very soluble in water? What's the difference? CO2 is not very polar? How about not polar? It's a linear molecule, with the carbon-oxygen bond moments canceling each other at the center of the molecule, which is the position of the carbon atom. But ammonia is not only quite polar because it has what shape? Shape of ammonia. Shape of ammonia. What is it? Trigonal pyramid. Beside being highly polar because of its trigonal pyramidal shape and non-bonding electrons collected on the nitrogen central atom, ammonia is also a molecule which exhibits, what is it?
Hydrogen bonding.
Yeah! You're damn right. You ever see the movie Dead Poet Society? Yes. Ha ha! Teacher Robin Williams takes one of his shy students, actually took the class, and he asked them to yawp. Remember that? Y-A-W-P. A loud, bold shout. When you know this stuff, I want you to yawp. Ha ha! Because you know it. And that's wonderful. ha! Alka-Seltzer. That's what Alka-Seltzer does. Liberates CO2, that's the bubbles. So guess what? Before we did this, we already talked ourselves through the chemistry and understood it. Because when this reaction takes place, we're making this as the product acid. This is the product base. And as we have just spoken about, this stuff is not very stable. And it readily decomposes into this and this, which in large molar quantity froths out of the system because it is not very soluble in water because of its lack of polarity. We just did it. All right? Wonderful. Okay? Now then, one molar sodium sulfide, excess, I forgot all this territory here. 1 molar ammonium chloride. We'll go down here for this. We're doing H. PSI first. One molar sodium sulfide solution. I'll start you with water. And sodium ion AQ. Now I want to know the other principal species in this system. What are they? You tell me the formula, I'll write it.
HS minus.
I'm hearing HS minus, hydroxide ion, and sulfide ion. One of those is dead wrong. Which one is dead wrong? Sulfide's dead wrong. You see sulfide ion on the acid-base table? What do you know about sulfide ion? It's a base which is strong. It's stronger than hydroxide ion. Which means if you put sulfide ion in water solution, the sulfide ion not only reacts with water to make hydroxide ion, that's why it's known as a base, sulfide ion, and hydrogen sulfide ion, which is the conjugate acid of sulfide ion. And the extent of that transformation is, practically speaking, what? 100%. So just because you see that label on the bottle, 1MNA2S, which means the solution was prepared by dissolving sodium sulfide in water, don't you dare think there's sulfide ion in that solution. You won't be able to find any by chemical analysis, because the sulfide ions added will have all reacted with water and become hydroxide ions and hydrogen sulfide ions, which all follows from now our developed knowledge of acid-base chemistry. All right, so there's our correct 1 molar sodium sulfide solution inventory, PSI. How about the ammonium chloride solution? Water, ammonium ion, chloride ion. What kind of pH will I observe for the ammonium chloride solution? Will it be greater than 7 or lower than 7 or 7? Well, the ammonium chloride solution. Show me acid quality, base quality, or neutral quality. Well, I'm asking. We agree on acid quality? Are you looking at the acid-base table? Are you recognizing that chloride ion, as we already know, is a base weaker than water? So the presence of chloride ion in water isn't having any impact on pH, on acid-base character of the system. But what about ammonium ion? Ammonium ion is a stronger acid than water. That guarantees this solution has got to be at least mildly acidic. And when we do more with the numbers part, when we get to that stuff, you'll find out that it is mildly acidic. pH of that solution would be about 5, something like that. Not very acidic at all. But nevertheless, we now know that when we examine our psi's. The strongest acid we got here is what? Ammonium ion. Strongest base? Hydroxide ion. Reaction, water is the product acid. And ammonia is the product base. Extent? Large. Bah! We said 2 equations. Now notice, I told you to consider mixing 1 molar sodium sulfide solution with this quantity of 1 molar ammonium chloride. What's this stand for? Excess, in abundance. So at the minimum, for the system we are presently considering making, we have to recognize that to this system, at the minimum, we are adding more ammonium ions than we are adding either hydroxide ion or hydrogen sulfide ion, or sodium ion, but who gives a damn? So we go back, re-examine the inventory. Since we had ammonium ion in abundance, in excess, and this is a large extent reaction, we have practically speaking wiped out the hydroxide ion from the inventory. So if we go back to the inventory, pick out the best acid, still remaining, ammonium ion. Now what's the strongest base? Look at the acid-base table. Look for the formula HS minus in your acid-base table. Do you see the formula HS minus appearing in each column? Yes, you do, don't you? But as an acid, the acid-base table tells you HS minus is a weaker acid than water. So we're not going to expect HS minus to do any acid stuff in water solution. But is HS minus a stronger base than water? You betcha. So it will be the other base in this system which will be able to react with ammonium ion. In this case, the product acid is H2S. And the product base is again ammonia. Tell me, have you any familiarity with the material H2S? Have you ever come across a sample of rotting or rotted eggs? Nice pleasant smell, don't you think? That's the stuff. You've heard about hydrogen cyanide, haven't you? Gas chamber gas. That stuff is more poisonous than hydrogen cyanide. More toxic. And you're going to deal with some of that stuff in the lab this term. But the human olfactory system is so highly tuned, so highly sensitive to hydrogen sulfide, you can pick it up on parts per billion in air. And your natural tendency is, rotten eggs, I run away. And that's good. Because if this air that's tainted with hydrogen sulfide starts to smell sweet and nice to you, you got a serious problem. You've just been poisoned. Don't worry, that's not going to happen to anybody. I've been running this investigation in this lab since I took over running it in 1987. We have had no problems yet. And I expect to have no problems ever. Because I can rely on you folks after if I jump up and down and holler enough to be careful. Okay, now then. What's the extent of this? Small. Now one more question. You see this formula? Chemical company manufacturers have a habit of writing strange formulas on occasion. I still see chemical company manufacturers selling bottles of ammonium hydroxide. There's the label, the formula, that label on the bottle. Well, there's another formula label, ammonium sulfide. You believe this label? Does this label represent something that's real? You see this reaction? This reaction tells us if you put ammonium ion in contact with hydroxide ion, you get an acid-base reaction which is large extent. These ions, ammonium ion and hydroxide ion, these ions, ammonium ion and sulfide ion, are not compatible. They kill each other. So you can write formulas like this all you want. That won't make the stuff exist. Are you following this? Beware of these bogus formulas. When you see a formula that you know from experience, which we're presently developing for you, you see a formula that's composed of a Bronsted acid and a Bronsted base, you get out your acid-base table. Because if the Bronsted acid part of that formula reacts with the Bronsted base part of that formula to a large extent, forget that formula. It's a lie. It represents something which cannot be made. Period. Everybody is supposed to ace now. Quiz 1.